block ciphers, a very brief tutorial. So please welcome Feistel.
Alright, so you guys have a challenge to keep me awake now because it's almost midnight my local time. So this presentation, I wish we would have some more interaction. You're not here just to listen, right? So try to interact with me whenever you have any questions. Just feel free to interrupt me and ask questions right away. So Dr. Abdurrahman was presenting stuff that would, if you look at the crypto primitives, what the talk of Dr. Abdurrahman was focusing was in this area. It was on public key primitives. What I'm going to speak about is symmetric key primitives. In particular, I'm going to speak about symmetric key block ciphers. I'm going to speak very little about how to design them, but I'm going to spend more time on how to break them. So I'm guessing that you're all familiar with symmetric key cryptosystems. So in symmetric key cryptosystems, we assume that both the sender and receiver share a secret key. So unlike public key cryptosystems where we have the notion of private key, public key pairs, and here we only have one secret key shared between the sender and the receiver. The main advantage of symmetric key cryptosystems is that they offer high data throughput compared to public key cryptosystems. So we're always providing encryption speed that is orders of magnitudes faster than public key cryptosystems. The other advantage is that they have what we call small footprints. So if you're trying to implement encryption algorithms on resource-constrained devices, then symmetric key cryptosystems would provide a very good option in this case. On the other hand, nothing comes for free. We always have to depend in the initial key distribution stage on public key cryptosystems because we're always suffering from key management problem in the case of symmetric key cryptosystems. So if I have a system of n users, I have to manage something in the order of order n squared keys. For example, just think of a university with 1,000 students in it, then you need to manage 1 million keys, which is certainly not a very easy thing to do. And that's why we use public key cryptosystem to do the initial key distribution, and then we use symmetric key cryptosystem to do the bulk encryption. So the problem of designing block ciphers is actually a very simple problem. Our objective is just to design a very large lookup table. So if you are able to design a very large lookup table, your problem is done. And this lookup table should act like a pseudo-random permutation. In particular, it should act like a keyed pseudo-random permutation. But if this problem was so easy to solve, I wouldn't be talking in here. So if you look at, again, like if this is my block cipher, just think of it as huge permutation, huge bijective mapping. So just to give you some feeling of how large it is, suppose I have a block cipher, and this is the input as a black box. I can think of my block cipher as a box where I have plain text coming in, cipher text coming out, and it's keyed, which means that I would also have a key. So typical length for the block sizes would be something between 64-bit to 128-bit, or even some ciphers now have 256 bits. And typical length for the key would be something around 128 bits up to maybe 256 bits. So suppose I would like to design this by just creating, I'm just going to buy enough memory and I'm going to design my cipher in this very primitive way. I'm just going to have very large memory and fill it with random permutation of the elements from 0 up to 2 to the power n minus 1, for example. How much memory do I need to buy? Or maybe let me ask a question with a smaller number. Suppose my block size, suppose this is just a toy block size. And my block size is only 16 bits. Then how much memory do I need to buy in order to implement this mapping between 16-bit to 16-bit? It's 2 to the power 16, right? So I only need to buy 64K of RAM, which is okay. But now suppose I would like to do the same thing but my memory, I would like to improve, like to increase my block size so that it's a more serious block cipher to 128 bits. Then in this case, how much memory do I need to buy? 2 to the power 128. So that's actually a very, very large number. If you're not appreciating how large is this, the total number of atoms in the universe is 2 to the power 180. So basically, you can never even find enough atoms in the universe to manufacture the memory you need to construct this block cipher. So the whole idea again is that I would like to build this key, and remember that this is only for one key. Like this large number we just mentioned is only for one key. If I like to have a key length of 2 to the power of 128, then I need to multiply this number by 2 to the power 128. So certainly I don't have enough memory to construct my block cipher using this naive approach. So how we're going to do it? It's basically, again, my basic problem is how can I construct something that acts like a pseudo-random permutation without having to buy that much memory. So let's try one approach. Again, I'm just going to go to my toy example. Suppose now I have a toy block cipher that maps 4 bits into 4 bits. So now, how much memory do I need to buy if I'm implementing it in the naive way? It's just 2 to the power 4, right? So it's only 16. But suppose I'm so limited that even for me 2 to the power 4 is so big, I cannot do it. Then one way to do it is that instead of constructing your lookup table in one step, we can construct it from smaller blocks. So, for example, instead of buying like this large RAM, like this 2 to the power 4 RAM, I'm going to buy a small one, which maps 2 bits to 2 bits. And then I'm going to have 4 of them. And suppose I have a structure like this one, then now I have a mapping between 4 bits into 4 bits. But let's see if this is a good idea to do it this way. So again, remember that my objective is to construct a keyed pseudo-random permutation, which means that my table should be indistinguishable from a pseudo-random permutation. If you are interacting with this black box without being able to see what's inside it, you should not be able to tell that it's constructed from these small ones. So let us see if this is a good idea to do it. Like, given the assumption that I like my construction to act as a pseudo-random permutation, or to be indistinguishable from a pseudo-random permutation. So now let's assume that you are the adversary and you're playing a game by interacting with this system and this system. You're allowed to either query this system or query this one. But at the same time, you're not allowed to look inside. And we say that you won the game or you broke the cipher if you are able to tell me whether you were interacting with this one or with this one. So can you win this game if I'm constructing the cipher using this construction? Can you differentiate between this one and this one?
Yes.
How can you do this? If I have a yes from the back, can you tell me how? How would we?
The left 2 bits are changed and the left 2 bits are not changed. We know that the output,
Yeah.
the left 2 bits are changed.
Okay. So in here, suppose I queried this box with a plain text, and then I observed the output. Now I flip 1 bit in here, and my plain text now is the same as the first one, but it has 1 bit flipped. And I observe the output. So if this is a random permutation, you are expected to see half the output bits changing. On average, half of them will change. Okay? Because if you restrict more than half, then you're actually, that's not good. But on the other hand, if you are interacting with this box, and you put some, for example, you put all zeros in here, and you observe the output. Now you flip 1 bit in here, for example, you have 1, 0, 0, 0, and you observe the output. What are you expecting to see? You're expecting to see that 2 cipher texts should be identical on this side. Right? So now it's a very simple. You have just 2 queries to your block cipher, and you are able to differentiate it from a pseudo-random permutation, which in some sense can lead you to an attack that would break the cipher. We're going to see how we can do this after. So that's certainly not a good way of constructing a block cipher. But suppose I insist that we work with these smaller blocks. Can you figure a way that would allow me actually to eliminate this weakness that I just described?
Sorry?
Like suppose again, I'm insisting that I'm only going to buy these 2 by 2 S boxes. I'm not going to buy bigger ones. Can you fix my construction so that you are not, like as an adversary, you are not able to break it using these simple queries that we just mentioned? But even if I have a key, it wouldn't help in this case, right? Because I still have the same problem. If I flip 1 bit in here, nothing will change in here. So the easy solution that some of you are pointing to is that instead of having this permutation layer acting as a unity permutation, what I can do is that I can have this one connected to here and this one connected to here. And same, this one should be connected to it. So I should have just a stronger permutation layer. And if I do this, that weakness I just described would vanish. So actually, that very simple construction is a very strong construction, and it's one of the most famous architectures that we use to build the block ciphers, and we call it substitution permutation network. Why we're calling it SPN? Because it has a substitution layer, and it is followed by a permutation layer. And in fact, actually, this structure is so elegant that you can do lots of analysis for it. And it's so strong to the extent that if you just pick if you don't care that much about efficiency, you can just pick these S boxes. Like suppose you're working with, suppose it's a 64 by 64 bit block cipher. Then I would have in this case 8 S boxes. So these like little lookup tables, we're going to call them S boxes or substitution boxes because they just do some substitution operation. And if I have 8 by 8 S boxes, and I can have, if you see the way that the permutation layer is constructed, you can just imagine how it's going to work when I extend my dimension into 64 by 64. So in that case, I would have 8 of them. And if I can have enough number of rounds, I'm actually done. That block cipher is going to be a very strong block cipher. The only problem is that you need a large number of rounds. So a large number of rounds is somehow going to be translated into either larger hardware resources or larger time to do the encryption operation. So again, this very basic architecture is very strong one, and there are like many sayings. For example, I think one researcher named Luke O'Connor, in I think in late 90s, was saying any block cipher would be efficient as long as you add enough, or would be secure as long as you add enough number of rounds. But the main problem when you have enough number of rounds, it's going to be inefficient. But again, this is one out of 2 of the very famous architectures we use to build the block ciphers. Again, this one we still call it SPN, but the main difference between the first structure and this one that I showed you is that in here, instead of having a permutation layer, assuming that I have more computational power, instead of having just simple wire crossing, now I can perform a linear transformation operation. And some people use some theorems from coding theory to optimally design this linear transformation layer so that I can optimize the resistance of the cipher using a smaller number of rounds. So again, if I was using just a straight permutation, I needed larger number of rounds. But if I optimally design this layer so that I can diffuse any little exchange that happens here into a very large number of exchanges in the next rounds very quickly, then I can have smaller number of rounds and I achieve the same security level. And usually we do this with some linear transformation layers that are usually designed based on some generated matrices from coding theory. Basically, if you work in coding theory, the optimal linear transformation layer here would correspond to what we call MDS matrix, or the matrix that is used as a generated matrix for maximum distance variable. Another, or the second most commonly used architecture to build the block ciphers is what we call Feistel structure. So the Feistel structure is, Feistel is the name of a person. So the Feistel structure, this is just one round of the Feistel structure. So basically what you do, you divide your input block into two halves, and you take one of them, you don't do anything with it, you just pass it to the other side. And the other half, you pass it through a nonlinear function, and then, so this side is the one that you pass through a nonlinear function, and then you combine it with the input from the other side. So now suppose I have a block cipher with 128 bits. Then one round of the Feistel structure would be exactly like this, but now I have 64-bit coming here and a 64-bit coming here. So now what would I do with this f? Now I'm almost coming back to my old problem that I cannot have a Boolean function with very large number of inputs. So I have here f is it's a Boolean function that has 64 bits coming in. How can I build it? I can actually use the SPN structure that I showed to you to build this. So it's again, I'm just sort of decomposing my architecture so that I can use this. The only advantage, or not the only, one of the main advantages of this Feistel structure is that this f doesn't have to be invertible in order for the overall structure to be invertible. If you look at the SPN structure that I just showed you, remember when you do encryption, you have to be able to do decryption. So all your substitution boxes has to be invertible, and your linear transformation layer also have to be invertible. But in the case of the Feistel structure, you can actually prove that this structure is self-invertible even if f itself is not invertible. So in the early days, like maybe in early 1970s or whatever, this was a main advantage because you would like optimize your design to restrict the required area without having the restriction on your Boolean function that it is required to be invertible. So now this is just if you extend a larger number of rounds, this is how it looks. And one very famous block cipher that was designed using this Feistel structure is the data encryption standard. And again, in all of them you do the same sort of high-level construction that you divide your data into two halves. But the f function in case of the data encryption standard looks like this. For the purpose of this tutorial, we don't care that much for how it looks or for the internal structure. Just think of it again as if it's one round of an SPN, but it's an SPN without the requirement that it has to be inverted. Okay, so I showed you two structures for block ciphers. One of them is called Substitution Permutation Network. The other one is called Feistel structure. This would cover pretty much 99% of any block cipher you can see. So if you would like to classify block cipher architectures, 99% or even maybe more than 99% of them would fall into these two classes, the SPN or the Feistel structure. Sometimes we refer to this Feistel structure as DES-like structures, because the most famous cipher that was designed using this Feistel structure was the data encryption standard. Others is pretty much you can literally ignore, because there are pretty much there is no famous block cipher that is designed based on a structure that doesn't belong to these two. We can have like something like called generalized Feistel structure, but it's still a Feistel structure. And then inside it, you can have block cipher that uses S boxes, or some ciphers that do not use S boxes. Some of them uses mathematical operations to achieve nonlinearity. For example, you can use multiplication operations, or you can use even addition modulo some number, and you do rotation, you do XOR. So if you mix addition, rotation, XOR, this is it's called like just addition, rotation, XOR. addition starts with an A, rotation starts with an R, XOR starts with an X. So now we have what's called the RX constructions. So the RX constructions is another very famous way and that you would use to build the block ciphers without the need to rely on SBOX. So you achieve your nonlinearity by mixing these three operations: the addition operation, modulo some number, the XOR operation, and the rotation operation. If you have S boxes, then these S boxes can be fixed or they can be key dependent. And if they are key dependent, they can stay static throughout the execution of your encryption operation, or they can be dynamic. They vary while you are doing the encryption. They can change. But very, very few ciphers are based on this because it's very inefficient to do this operation. So now if you go and try to read about any block cipher, just pick any block cipher you hear about, you should expect that when you see it, it will either be an SPN or a Feistel structure. Modern block ciphers have some features in them. So some of the modern block ciphers come as a family of ciphers. For example, data encryption standard came with fixed dimensions. So the block length was 64 bits, the key length was 56 bits. But for modern block cipher, I give you a family of ciphers. I tell you that I can have a block length of either 128 bits, 192 bits, 256 bits. The key size can be 128 or 256, for example. So they come up, like some of them would come up with the option to vary the key length or the block length and the number of rounds. Of course, you don't mix and match. Usually the designer will give you the valid combinations of these. So you would expect that when I have a larger key length, I will have a larger number of rounds, for example. And they usually imply mixed operations. So this is what I call, for example, the RX constructions, where you mix the addition and rotation and the XOR operations. Some block ciphers were using data-dependent rotations or key-dependent rotations, where throughout the operations of the cipher, you would rotate your data depending on the data itself or depending on the key itself. But now we don't see that many of these because they were easily attacked using timing analysis. If I can observe how long would it take you to execute the cipher, and if the rotation operation, can think of the rotation like if I'm rotating by 1 bit, I would certainly take less time than rotating by 10 bits. Then these operations are sort of disappearing now. In terms of the key schedule, which is something that I haven't talked about here, but we just described how we do the encryption, but I didn't show how would you mix your keys with your data. So if I say that a cipher has, if I go to my basic structure, for example, in here, and suppose this were like each one of these S boxes was 4 bits to 4 bits. So this is a toy cipher with 16 bits coming in and 16 bits coming out. So now suppose my key, the user key is 16 bit. Now I need to take this key and somehow derive from it what we call sub-round keys. So I take this 16 bit and produce sub-round keys that will be mixed with the input to this round, input to this round, input to this round, and the output of the last round. So this operation that takes the user key and produces the sub-round keys, we call it the key schedule, or the key setup. It varies a lot from one cipher to the other. In some lightweight ciphers, this operation can actually be as simple as taking the user key, for example, and then just adding some constant to it in order to produce the other sub-round keys. In more complex block ciphers, you perform more complex operations to the user key in order to generate the sub-round keys. Okay, so now this is pretty much what I need to tell you about the design of block ciphers, because if you would like to be a good block cipher designer, you need to be able to learn how to attack it first, and then you'll be able to design good block ciphers. So I'm going to spend more time on cryptanalytic techniques or ways to attack block ciphers. So the assumptions we have whenever you do any cryptanalysis, whether it was on the case of public key cryptosystem or symmetric key cryptosystems, is that we assume that the attacker knows everything about the design of your system. So if you're using a cipher, he would know that, for example, you're using an SPN structure, he will know the S boxes, how they were constructed, he will know the key schedule, he will know the key mixing operations, he will know the linear transformation layer. He knows everything except for the key. And we also have some attack scenarios. So we can assume that, sometimes we assume that the attacker has access only to the ciphertext coming out of the encryption algorithm. But usually, this is a very tough test for the cryptanalyst, because in most of the modern block ciphers, there is very little you can do if you only know the output of the cipher. If you only have access to the ciphertext, there is very, very little you can do. And most of block ciphers, most modern block ciphers, will be secure if this is your attack scenario. But in real life, we actually have other attack scenarios. For example, I can assume that we have a non-plain text attack. And this is a very realistic scenario. Suppose you are encrypting a Word document, and the attacker has access only to the output of the encryption you only have access to the encrypted file. But if I know that your Word document is Word version whatever, like if you're running Microsoft Windows version 8 or Windows 8, for example, and you're most likely going to be using specific version of Microsoft, then the header of this file, I know it. Everyone will be able to know the header of the file. And if I look at the encrypted version of the file, then in this case, I have access to a ciphertext and its corresponding plain text, which means that I'm operating with this non-plain text attack scenario. Similarly, there are situations where I can give the option to the attacker to send some plain text and obtain the corresponding ciphertext. Or I can even, and this would go with two different scenarios. One time I asked the attacker, like when we were testing the security of the cipher, we say that, give me all the challenges at once. In the other case, in the adaptive case, you give me one challenge, and depending on the response you're getting from the encryption algorithm, you form your other challenge. Which one you think is going to give you more freedom as an attacker? This one or this one? The chosen or the adaptive chosen? The last one, right? Yeah, I think all of you is familiar with the 20 question game. Like I pick something, I keep it secret, and then you ask me 20 questions, and then you should be able to tell what did I pick, right? And you always form your questions based on the answer I gave to you. You ask me one question, and then I reply to you, then you adaptively change your next question, right? You're very likely to win this game if you are able to do this adaptation in the way you're forming the question. But if I restrict you to ask all your questions at once, you're very unlikely to win this game. So this certainly the adaptive chosen plain text ciphertext model is the most powerful one from the attacker perspective. Okay, so when we judge the security of a block cipher, we always have, it's almost a game. And the rules of the game is very well established. So we say that the most naive way of breaking the cipher is to exhaustively break, like just to go through all the possible keys. So if I have a cipher with 64-bit keys, the exhaustive search would just be as simple as exhaustively searching all the possibilities of the key, 2 to the power 64. You give me one plain text and its corresponding ciphertext, and then I just exhaustively encrypt the plain text with all the possible keys until I have a hit with the ciphertext. If I have a matching plain text ciphertext, I say that I have used the right key to do the encryption. But again, this is a naive attack, because if you just have enough, if your key length is long enough, then the attacker cannot win this game. So we always judge the security, or like we judge the success of the attack based on whether the effort required to break the cipher is less than 2 to the power k, or if it's less than 2 to the power k, we say that it's a theoretical break. If it's a really small number, then this is really a total break of the cipher, or a practical break. So the attacks are usually classified into two large classes. One of them is what we call mathematical attacks. So all you have to do to be able to execute this attack is just to have a piece of paper with the description of the cipher, and you try to analyze the internal structure of the cipher and try to break it. Examples of these are the very famous examples of mathematical attacks. So in this talk, I'm going actually to talk about these three examples: differential cryptanalysis, linear cryptanalysis, and saturation attack. There are actually more interesting attacks if you're coming from engineering background, which are what we call implementation-dependent attacks. So in this case, I assume that I have access to the device that's doing the encryption, and I assume that I can observe, for example, the computational power that is consumed by the device. So I can perform some power analysis. And if I can correlate the power analysis with the internal operations of the cipher, then I might be able to recover the key. Or if I can measure the time required by the device to do the encryption, I might be able to recover the key. So this is the timing attack or differential power analysis attack. Even if I can hear the sound of the computer that's performing the encryption, I can correlate this sound with the operations performed by the computer. And this is what we call acoustic cryptanalysis. Or maybe I can inject some fault in the device while it's performing the encryption, observe the faulty output. By comparing the faulty outputs with the correct output, I might be able to recover the key. But the main advantage of the implementation attacks is that usually the computational complexity associated with the attacks will be very small. But the main disadvantage is that they require high-tech equipment in order to be able to execute them. On the other hand, this class of attacks is good for mathematicians because you don't need any equipment. All you need is just a piece of paper. You need to study the structure of the cipher. Unfortunately, most of the time for the modern block ciphers, the complexity of the attack will be very high. But again, as a rule of the game is that if my block cipher has a block, as for example, a key length of 128 bits, even if my attack would require complexity of 2 to the power 120, you win the game. You have a paper actually. So the beauty of this field is that the rules of the game is very well defined. If the key length is 2 to the power k, as long as you can break your cipher in 2 to the power k minus epsilon, you won. Whether that's we usually call it a theoretical break. If you can push this number to something around 2 to the power 50, 2 to the power 40, this is a practical break. But nevertheless, from academic perspective, the rules of the game in the community is very well established. For a cipher with with key length k, as long as you can break it with less than 2 to the power k operations, this is considered as a successful attack.
How about breaking the root attack?
Say that again?
How about breaking the root attack?
No, the brute force is 2 to the power k, right? So as long as you're less than brute force,
And if my analysis is almost working the brute force capacity.
so I'll just give you an example. The best attack on AES 128, which means that the advanced encryption standard with key length 128 bits. So the brute force is 2 to the power 128, right? The best published attack on it would require complexity 2 to the power 126 point something. So this is, for me, they are both infinity, right? But again, given the rules of the game, as long as your complexity is less than 2 to the power 128, it is acknowledged as a successful attack. And these results are published in top conferences. The leak attack is one of the, again, like if you ask anyone in the area of symmetric key cryptosystem, it is the only attack that was able to break AES full number of rounds, and we still call it break, right? Although practically it's not. So you always have to differentiate between theoretical break and academic break. Theoretical break or academic break and practical break.
But actually, practical break is much more easy, right? Because you have some more information. You have for example, somebody can use an attack and use differential attack or mining with a type with a second attack. You can break faster.
But the only, there is major differences in here, right? Here I need to be able to access the device while it's doing the encryption.
It's not easy to access. Normally people can access the device. Right?
It depends, right?
For example, you have a same version and you're running in the same cryptographic scheme, And you have a SIM key, but
No, I can give you an example. Like in many cases, actually, you have access to a device, but you're not allowed to know the key. For example, the smart card you have in your pocket, you own the card, but on this card there is a signature key that you're not supposed to know. Although you are the owner of the card, but you're not supposed to know that signature key. So I can observe the signature operation, and I can recover the signature key. Right? But in many other cases, so this is just one example for the case where implementation attacks will be useful. Like if you're attacking a smart card, that's a very...
Sometimes what we do is people using cheat the CPU, and then you can get more information to help in differential changing the hardware, still memory things, but changing the hardware, and it will surgical attack.
But again, you shouldn't compare apple with banana, right? Because sometimes if all what you have access to is encrypted file, this is completely useless. Right? Because if you only have access to the file after it's an encrypted file, right? I have no idea how it was encrypted, but I need to know the key which was used to do the encryption.
But the scheme with that I'm from the industry, one of the things I work is on the automotive security. So this means people have the same key, but the only difference is the key. People can break using the hardware knowledge, and then you use the hardware knowledge to use for the theoretical. Normally people use the theoretical hardware. Then using the hardware knowledge as it we have to do this in space, right?
Yeah, and maybe I'm just going to emphasize that even when you're performing these attacks, you are actually making use of some of these attacks.
Yeah. It's combined.
Yeah.
Just more on the reality work, not just algorithm.
Yeah. So let me now try to start talking about differential cryptanalysis. So, or even before I go to this is a very long list. And I can add more, like you can just go beyond this slide with adding more theoretical attacks. However, all the mathematical attacks against block ciphers, they have all of them have the same high-level structure. So in all the mathematical attacks against block ciphers, what we try to do, suppose just as an example, I have a block cipher that has 4 rounds. And one feature of block ciphers is that they are always constructed by multiple rounds. Right? So there is no block cipher that's just one step. So the notion of iterative block cipher is always there. So no matter what block cipher you're dealing with, you have some iterations, some rounds. So now all the attacks against these block ciphers would have pretty much the same high-level structure. So what you try to do is that you try to find some distinguisher or some distinguishing property that will hold for a reduced round version of the cipher. So if I can find some property that would hold, even with some probability, even with very, very small probability, it's okay. If I can find some property that would hold for a reduced version of the cipher. For example, in this case, I'm trying just, for this toy example, I'm trying to attack a cipher of 4 rounds. What the attacker would try to do is to find some property that would hold for 3 rounds. So suppose, don't think of this property for now. Just think that I have magical thing that allows me to find some magical property that would hold for some relation that would hold between maybe some differences in the plain text here and some difference in the output of this round. If I can manage to find this distinguisher, I am able to recover the keys of this cipher. How would I do this? The idea is very simple. So suppose I have this distinguisher and I know that it holds with some probability between this round and this round. There is some probabilistic relation between the input to here and the output at this level. So what I'm going to do, I'm going actually to guess the value of the key of this round. So if I guess the value of the key, this is the only unknown here. So if I guess it here, I can peel off the last round. If I peel off the last round, I can test whether my property holds or not. If my property holds, it means that my key guess is correct. But if my property does not hold, it means that I made the wrong guess. So basically, this is how you're going to attack the cipher. Because again, if you try to attack the cipher by guessing these sub-round keys, suppose each one of them, for the sake of example now, I have 1, 2, 3, 4, 5. So suppose each one of them was 10 bits. Then, if you're trying to guess them, I need 2 to the power 50. But if I'm able to guess each one of them and confirm whether my guess is correct or not, one step at a time, then now I'm going to recover K4 in 2 to the power 10. But I will be able to know the right value of K4 after I'm done. Then I'm going to recover K3 using 2 to the power 10 operations. So my overall complexity now is 5 times 2 to the power 10 instead of 2 to the power 50. Are you getting it? Okay, so the main idea again is to find a distinguisher that will hold for a reduced number of rounds, then get the last sub-round key and confirm whether my guess is right or wrong, and then I can just keep dealing the sub-round keys. So all the attacks I'm going to describe, eventually they are going to look like this. Eventually I'm going to have a diagram like this. The only difference is that for each attack I'm going to use a different distinguisher property or a different distinguisher. The distinguisher will be different from one attack to the other. So when we're talking about linear cryptanalysis, I'm going to use a linear distinguisher. When we talk about differential cryptanalysis, I'm going to use what we call differential distinction or differential characteristic.
Is it a sub-key or a main key?
These are sub-round keys.
Key, sub-key.
Yeah. And usually for most of the ciphers, it depends on the key schedule. But most of the ciphers, like some of them, if you are able to recover one sub-round key, even like for example the advanced encryption standard, if you are able to recover one sub-round key, for AES 128, you recover the user key. You recover this. Pretty much you recover all the keys. Okay. I promise we will go for lunch at 12:30 exactly. So just 5 more minutes and you're free. Okay, so let's look at very basic example of differential cryptanalysis. So suppose I have a very simple cipher, like that small S box. Suppose it's a toy cipher. And I give you the S box. So the S box is just a bijective mapping between numbers like 0 to 15, and it produces permutation for these numbers. So suppose this is my cipher. I have my S box. I have my plain text coming here. I XOR it with K0. Then I take the output of this box. I XOR it with K1. So suppose K0 is 4 bits and K1 is 4 bits. So if you try to exhaustively search for the right key, if I give you some plain text and their corresponding cipher text, how many key guesses you need to do in order to break this toy cipher? This is 4 bits and this is 4 bits. So what is the total number of keys that you need to try in order to break this one? In a very naive way. 2 to the power 8, right? So just do an exhaustive search for all the combinations between K0 and K1. So can we do better? Can we find the key in less number of, like less effort than trying all the 2 to the power 8 possibilities? So suppose I have one plain text and its corresponding cipher text. This is B0 and C0. And I also have P1 and C1. So I have 2 pairs of plain text and cipher text. So here, for example, I tell you that when my input was A, the output was 9. So the input and the output are in hexadecimal notation. And when my input was 5, the output was 6. Can I break this cipher in smaller number with small computational complexity? So suppose I know that my plain, like this is the first plain text cipher text pair, and this is the second one. In order to know the difference in delta U, so I suppose this is B0, I'm going to call the corresponding U here U0, and this is I'm going to call it V0, and this is C0. When this is P1, U1, V1, C1. Okay. So suppose I ask you to get the difference between the XOR difference which is just you store the two values, between U0 and U1. Can you get it without knowing K0? So this U is what? Is P XORed with K0, right? And so U0 is P0 XORed K0. And U1 is P1 XORed with K1, it's K0. So actually the key can cancel out. So I can know the difference in U, or I can know U0 XORed U1 without knowing K0.
Yeah, we can do that.
So it's just very simple XOR operations. I can know the U0 XORed U1 without knowing the value of K0. So if you do this, just XOR this value A, XOR it with 5. If you just quickly, the A is 10, 10 in binary, and the 5 is 1, 0, 1. So when you XOR them together, you get F, or you get all ones. So the difference here is F, irrespective of the value of K0. So now I know that the difference in this point was F between U0 and U1, irrespective of the value of K0. So now what I'm going to do, I'm actually going to guess the value of K1. I'm going to exhaustively try all the values of K1. So when I suppose I have guessed K1 as a 0, then I can tell what was the value of V in here. I can evaluate the value of V0. And I can evaluate the value of V1 as well. So when I know the value of V, I can actually go backward because I know the S box. I can do the SM versus operation. So what I'm going to do, I'm going to guess the value of K. Based on my guess for the value of K, I'm going to evaluate V. Based on my evaluation of V, I can evaluate SM versus of V. So I'm going to do the same for both values of P0, of C0 and C1. So now when I do this, I can propagate to here and then to here. I can actually calculate the difference in here. And then I know that this difference has to be F, without knowing the value of K0. So if you look at this table, it's basically, this is what I'm going to do. I'm going to use the fact that I know the difference here is F. I'm going to get the value of this key, then propagate the knowledge of the ciphertext to this point, and then evaluate SM verse to get to here, and then evaluate the difference at this point. So if you do this, you're going to find that only for two guesses of K1, the difference is F. So you know that the only valid guesses for K1 must be either 7 or 8. So now we know that for sure that the right value of K1 is either 7 or 8. Now I know actually, once I know that the K1 is either 7 or 8, I can go back, evaluate U0. So at this point I know some value in here and I know some value in here. So this one will be calculated actually. I don't have to guess it anyway. So instead of trying 2 to the power 8 possibilities, I only try 2 to the power 4. And this will filter out the right key to only 2 possibilities, and I'm only going to have another 2 possibilities for this one. Then I'm just going to try the encryption of the value A with the combination of the K0 and K1, and the right combination will give me the value 9. So the point is that using differentials between the inputs allow me to bypass some keys, which allows me to have a more efficient recovery of the sub-round. Right? If you didn't get it, I'm going to repeat it quickly when we come back after the break, and we're going to see more of this. Do you have any questions before we break?
Thank you, Professor. So this is the end of our first session with Professor. We will have our lunch break now. The lunch break is at the same place where we have a tea break just now.